pleasure to introduce our speaker for today, Nick Rozenblyum. We'll be talking about geometric applications of infinite dimensional representation theory. So, Nick.
Thank you. It's a pleasure to be here. Thank you for the invitation. So what I wanted to do today is talk about, well, some geometric applications of infinite dimensional representation theory, which is a sufficiently vague title, I think. I can do almost anything. But before sort of getting to that, I'd like to start with a slightly more classical story of how finite dimensional representation theory fits into algebraic geometry and how one thinks about varieties using Lie algebras, essentially. And what we'll see is that this infinite dimensional story is a slight generalization of this, but which takes into account some structure on curves or higher dimensional varieties, and the structure will allow us to do new things. So let me start with some remarks on deformation theory. So I guess it really started out as a philosophy more than anything else. And the philosophy is due to a large number of people. Deligne, Drenfeld, Fagan, Hinich, and others. And the idea is that infinitesimal structure, infinitesimal geometry, is governed by differential graded, let's not worry about that, Lie algebras. So these tend to be sort of relatively small, finite dimensional Lie algebras. So what do I mean by something like this? Well, so maybe let's take the first example that one ever encounters of a Lie algebra, which is well, let's say we have some variety or a manifold. Then we consider, so let's say over C, then we can consider vector fields on X. So take this in a notation. I'm just going to call this the global sections of the tangent sheaf. So this vector space has the structure of a Lie algebra. In the case that X is compact, in the algebraic geometry world, this is a finite dimensional vector space. So this has the structure of a Lie algebra. And perhaps one way of thinking about this Lie algebra, is I'll put this in quotes, is it's the Lie algebra of the group of automorphisms of this variety. So you can think of automorphisms forming some kind of an algebraic group, and this would be exactly its Lie algebra. So what does that have to do with deformation theory? Well, the group of automorphisms really tells you something about the space of the deformation space. So this Lie algebra, so that X.
It's always an algebraic group?
Well, I'm being vague about what I mean by an algebraic group.
All right.
In the case of in the case that X is proper, then this will be finite dimensional, and this really will be an algebraic group.
Okay.
This really will be its Lie algebra. Although I want to consider more general situations. It can be, for instance, infinite dimensional. So this is the G Lie algebra, is the Lie algebra. Describing the deformation space of X. near the trivial deformation. So that's sort of a particularly geometric way of thinking about the Lie algebra of vector fields. So let's say this is the first example. The second example, well, all of these are going to have the same kind of flavor. And so the second one is going to be a relative version of this. So suppose I have a point in x. Point. And then we can consider, rather than, we can take the tangent space at this point. Now, really, we do need to consider dg and shift it by 1. So I take loops on it. This has the structure of a Lie algebra. dg Lie algebra. Well, I don't want to say too much about where that comes from, at least not yet. This has to do with a kind of causal duality between commutative algebras and Lie algebras. If you think of x as being some kind of an affine gadget, then this is really the causal dual Lie algebra.
Why are you shifting it by 1?
No,
I'm just philosophically.
Oh, philosophically. So philosophically, this. So in terms of kind of deformation theory, what this Lie algebra does is it describes not the deformations of x, but the deformations of this point inside of x.
Ah, okay.
So what you can well, a bit of an aside. So you can imagine. I don't want to say what I mean by this object. You can imagine considering the loop space at x of x.
Right.
And so, well, let's just, one can make these kinds of arguments precise, but let's just go by analogy for a moment. And this has the structure of a group. So this is a group. And then this shifted tangent complex. Oh, by the way, I should say that if x is not smooth, then this...
you got to be careful because that could be a singularity, and you could actually get into trouble whenever you take the tangent space at a singularity.
Oh, well, one has to be careful about these things, but it's never really a problem.
Oh, I see.
And so this is the Lie algebra. Is the Lie algebra? I'll put it in quotes. Of this group that I didn't really define, of this loop space. So this, what this is, so this is supposed to be the Lie algebra of automorphisms of this point inside of x. So, you know, maybe this would be more familiar if x was something like a stack where points are already allowed to have automorphisms, and then this might even be something in degree 0. So this Lie algebra, this is the Lie algebra of automorphisms of x inside of x. So it's sort of a relative version of, rather than deforming a variety, we're deforming a map. So the point is, this Lie algebra, in some sense, describes the formal neighborhood of x. So it doesn't know very much about x, but it knows about everything infinitesimally close to this point. So maybe, having said that, maybe it would be a good idea to spell out a little bit more explicitly what I mean by, well, it describes the formal neighborhood, or that it governs some deformation theory. So some facts. So one fact is that really let's work with this guy. By the way, this first example was a special case of this, where you consider the deformation space, and then X is a point in that. And if you apply this construction, you really do recover that algebra of vector fields. Now, so this is in some sense more general. So we can look at the Lie algebra cohomology. This Lie algebra. So this forms, well, a priori this forms a differential graded algebra. It has an augmentation ideal, so let's complete it. By this, I don't want to say too much about that, but by this I'll mean the completed version. And so we can take its formal spectrum. So this is going to be exactly the formal completion of X at X. So there's a sort of a precise relationship between the formal completion and this Lie algebra. It really does tell you what. I hope that makes sense. So another so I said something about representation theory. We can consider representation theory of this Lie algebra. And you can ask, what does it correspond to geometrically about this formal completion? So modules over this Lie algebra. These are the same as incoherent. In parentheses, I don't want to say too much about that. So these are some kind of sheaves on this formal completion. So usually in algebraic geometry, one considers quasi-coherent sheaves. There's a slightly different version of it called incoherent sheaves, and I don't want to say too much about that, but the point of incoherent sheaves is that's where growth index Serre duality naturally takes place. So in general, if you think about growth index Serre duality, there's a problem defining sort of the upper Schrick map when your map is not a finite Tor amplitude, and sort of changing slightly the category of sheaves fixes this problem. And this is precisely the category that's seen by considering these modules. Going a little bit further, so the trivial module under this equivalence, this corresponds not to the structure sheaf, but to the dualizing complex. This formal completion. So the way this category of incoherent sheaves is built, that the canonical choice of object here isn't the structure sheaf. But
so you're dealing with differential ideals at this point, right?
What's that?
You're dealing with differential ideals at this point, no?
Differential ideals.
Because you said the sheaves on. Oh no, I'm sorry, no.
No, these are. This is a formal spectrum of some ring.
Right.
But if I just said coherent sheaves, what that would mean is this would mean so take that ring as a topological ring, and consider modules, which are discrete, and that the action of this ring on this discrete module with its discrete topology is continuous. This is some sort of a slight modification of this. So this corresponds to the dualism. And the other thing, the other important point I wanted to make is that the Lie algebra homology so this corresponds to sheaf homology. So anytime on one of these kinds of things, one says a sheaf, you can just immediately transfer yourself over into a representation theory of a corresponding Lie algebra, and you have this dictionary of operations. So maybe as a special case of this, if you take the trivial module and you take its Lie algebra homology, so that's just what is usually called the Lie algebra homology of the Lie algebra. So this, as a result, identifies with the formal, with a space of formal distributions on X supported at this point. All right, so that's really most of what I wanted to say about deformation theory, at least in the context of looking at varieties. So so really, to implement this philosophy, to say that differential graded Lie algebras are the same as certain kinds of moduli problems, or moduli problems, near some point, one needs to enlarge the class of spaces that we consider to not just varieties, but something bigger. So let me define a moduli space, or sometimes just space, when there's no ambiguity. So this will be, so by this I will mean a functor from the category of rings over some field. So K will be, let's say, an algebraically closed field, field of characteristic 0. So you can safely assume it's the complex numbers. So from rings to sets. So just as an aside, this isn't really what I mean. For if this makes sense, what I really mean is some derived version of this. So I want to derive in sort of two directions. I want to allow for things more general than sets. Namely, I want points. I want to allow some stacky phenomena. So points can have automorphisms. I'll give some examples of that. And I want the rings to also be. I want to allow the rings to also have some derived nature. So really, it's going to be some homotopical version from commutative differential graded algebras over K, which are concentrated in negative degrees, into simplicial sets, which also has some kind of homotopical nature. But I don't want to sort of get into this whole world of derived algebraic geometry. That will really be on the periphery here. So I wanted to satisfy two conditions, which I will say only vaguely what they are. So there's some finiteness conditions. There's a finiteness condition. So it can't be too big. It's something like almost a finite type in varieties. And the other is I wanted to have having good obstruction theory. So, in some sense, this is the second condition is rigged so that this kind of deformation theory story would work, although it's slightly different formulation. So that's all I will mean by moduli space. So, just to, if you're not familiar with this, just to convince you that we haven't really gone all that far, is that if X is a variety, we get, so first example, if X is a variety, then we can regard, I don't know, M sub X maybe, as a functor from rings to sets by considering a ring R goes to home from the spectrum of this ring into our variety X. So for instance, if X was the affine space, this sends any ring to just the underlying set, and so forth. So this is this functor of points approach to algebraic geometry. And well, so maps between these in this category are the same as maps of varieties for formal reasons and so forth. So that's the first example. Another example, let's say again X is some variety. G is an algebraic group. I'm going to define this moduli space called Bun-G of X. So as a functor from rings. Now, let me be a little bit more honest. It's not going to be a functor from rings to sets anymore. It's going to be a functor from rings to groupoids. So then Bun-G of X of R. This is going to be principal G bundles on spec R across X. So this just classifies principal G bundles on X, essentially. Another example is going to be, so if X and Y are varieties, so this is going to be an important space later on, maps from X to Y. So valued at R, this is just maps from X cross spec R to Y. Oh, sorry, so again, this is just, so complex points of this, for instance, are just going to be exactly the maps between X and Y, and this gives it some kind of extra structure. The last example that I want to mention is just let's call it def, which is probably the first example of a moduli problem that one encounters. Defs of X, so deformations of a fixed variety. So this is going to be the space of deformations of X. Deformations of X over spec R. So these are the kinds of things we'll consider. And the last thing I'll say is that there's a notion of a formal moduli problem, a formal moduli space, which I'll define in a slightly non-standard way, which is going to be a moduli space with the condition that evaluated at the ground field, then this is just a point. So it has one closed point, essentially. So if M is a moduli problem, a moduli space, and X is a point, then there's a procedure which takes this guy and creates the formal completion at X. So formal completion. And the point is now this is a formal moduli problem. Formal moduli space. So the offshot of this discussion is a theorem, which I think is due to Hinich. There's an equivalence between formal moduli spaces and differential graded Lie algebras. All right. So, and the equivalence goes along the lines that I sort of indicated before. So that's all good and well, and this maybe says something local in your point about say a variety or a moduli space. But maybe we want some more information. Maybe we want to use this to get some more information. And the way we can do that is by observing that there's a sort of a close relationship between formal completion and some kind of differential operators. So, just a little bit of differential geometry. Well, differential operators. So, all I will say is that, well, there's this ring, D sub x. So x, let's say, is still a variety. This is a ring of differential operators. And we can consider sort of dx modules. So that's going to be a sheaf on x. Let's call it V on x with an algebra map dx tensor V to V, so that it becomes a module, the usual kind of thing. So what sort of objects are these? Well, so these generalize two ideas, which are maybe the same idea. So generalize two ideas. One is the notion of a vector bundle with a flat connection. So in particular, if you have a vector bundle with a flat connection is a map from, is a covariant derivative from V into V tensor. One forms, sort of dualizing that. You get a map from the tangent space cross V into V, which the fact that it's a flat connection implies that it extends to a map like this. And the second idea is of a system of differential equations. I should say linear. Sorry, of linear differential equations. So D modules are sort of a coordinate-free way of talking about systems of linear differential equations on X. So what do I mean by that? Well, you know, let's say X is A1, and then, you know, suppose we wanted to describe some differential equation. Let's say f prime equals f or something like that. Then we can construct the D module. Well, it's by generators and relations. It would have a single generator, so f is a generator. And the relation would be that, well, d sub x sub f. So this d sub x is the thing corresponding to the vector field with, let's say we picked a coordinate called x, maybe I'll call it t. On A1, that this is equal to f. And so this generates some D module. And so solutions are exactly maps from this into the structure sheaf as D modules. So this kind of gives a coordinate-free way of talking about these things. So the canonical example is the structure sheaf. It has a structure. Module. So just by differentiating functions. So for our purposes, it will be, so far, this looks quite different from what I've been talking about before, of course. But so, to kind of connect it up, I'll say that for our purposes, it will be more convenient to consider right D modules rather than left D modules. So this D is a non-commutative ring, so we can consider left and right D modules. In this case, both are equivalent. So there's a canonical example of a right D module, which maybe I'll call omega sub x. So this is top forms. So the structure of a right D module is given by the Lie derivative. And so interchanging, so there's the categories, as abstractly, the categories of left and right D modules are equivalent. but they don't preserve kind of the underlying sheaf. So for instance, under this equivalence, O goes to omega. And in general, it's implemented by tensoring with omega, or omega inverse. So the point of telling you this is that there's a reformulation of the notion of D-module due to Grothendieck by considering the infinitesimal groupoid. So there's a groupoid where we take, there's kind of a trivial groupoid where we take the square of x. It's got the two projection maps, but we can take the formal completion at the diagonal. So this is formal completion at the diagonal. And the statement is that modules, sheaves equivariant with respect to the infinitesimal groupoid. These are exactly the same as B modules, so I think they're right. So let me spell out a little bit more explicitly what it means to be equivariant. So suppose I have some sheaf. Let's call these P1 and P2. So equivariant roughly means that the two pullbacks of this sheaf are, well, it's the data of an isomorphism. And then there's some coherence. So this is this idea that if you have kind of the idea behind this equivalence is that giving a flat connection on something is the same as being able to do parallel transport. Well, this doesn't a priori make sense in algebraic geometry, but you can do parallel transport infinitesimally far. So what that tells you is it identifies the fibers of your sheaf at infinitesimally nearby points, and the universal example of infinitesimally nearby points is this formal completion of the square at the diagonal.
So the fibers are isomorphic at infinitesimally near points?
Yes, and it's the data of the isomorphism that gives the structure of the D module. So the reason this is this is a good idea so now I can sort of relate this to what I was talking before is because we can regard this formal completion of x squared over x, well, let's pick a projection, let's say P1, as a family of formal modular spaces. So it's some relative version, and such a thing is governed by a sheaf of Lie algebras. So the sheaf of Lie algebras is going to be the tangent complex, again shifted by 1. Now we haven't picked a point. If we were to pick a point, the fibers here are exactly the formal completion at that point. So this is a sort of a way of passing between kind of differential phenomenon and deformation theory. All right. So that was supposed to be the introduction to things. But so now, let me tell you the direction in which I want to generalize this story. So this is going to be the, so above is going to be the n equals 0 story. So in general, I want to consider the following kind of thing. So we're not only going to study moduli spaces anymore, but I want to consider moduli spaces that depend continuously on some variety of a fixed dimension. So first of all, consider this category, var sub n. So these are going to be smooth and dimensional over K with, so the only maps I allow are étale maps. So these are essentially open embeddings or coverings thereof. And I'm going to define what a continuous family of moduli problems, moduli spaces is. Let's call it, well, let's say a definition of continuous moduli. Moduli functor. Functor is a functor. Let's call it script M maybe from so to every variety. Opposite. So to every variety, we associate some kind of moduli space. And if we have a map of varieties, there's a map the other way of the corresponding moduli spaces. And I want this functor to satisfy two conditions. One is that it's a sheaf. So in other words, if we have a covering of a variety, we can recover the moduli space by some gluing procedure. And the second is this continuity. What that means is that if we have some base S and we have a family of varieties, what we get, then applying this functor, is sort of, well, we can apply it pointwise, but the point is these glue together to a family as well. So this is what I'm going to mean, some family moduli spaces. So this is so these are the kinds of things I'm going to consider. So if you notice, in many of the examples, there was some of moduli spaces that I gave. There was some dependence on a different variety. And the point is, we want to not only we want to study how those change as we change the variety. So some examples. So let's say X is a well, first example. So G is an algebraic group, sort of bungee of blank from n-dimensional varieties. So if you have a map and you have a G bundle on the target, you can pull it back. G source. So this is an example of such a functor. You can check. It satisfies the sheaf condition. So if Y is a variety, another important example is maps from blank into Y. Let's see, and I think the only other example that I'll give is deformations. Deformation space is also an example. So it associates some variety to its deformation space. This also satisfies these conditions. So the first, so similarly to, well, so let's do the first part of, let's talk about the first part of the story that I gave, namely deformation theory. So suppose X is some n-dimensional variety. Then, then we can consider the moduli space M of X. And let's say we have some point in here. Call it P. So let's say we want to describe the formal completion of this moduli space at some point P. Of course, we can just treat it as by itself as a moduli space at some formal completion. The previous story applies completely. So what more can you possibly want? Well, one kind of structure that you might want to have is maybe you want this formal completion to have some kind of local nature on X as well. So maybe we want to study this by not only studying it globally, but also taking into account the geometry of X itself. So such a thing as, well, I'm going to call a continuous formal moduli functor. That's sort of the first theorem. Stages, there's an equivalence. So it's really sort of a refinement of this theorem of Hinich between continuous formal moduli functors. Well, I guess dg. Oh, let me state it like this. So let me state the n equals 1 case. So most of the example, so the main example that will hopefully get to in a few minutes is going to be for curves. So that here n is equal to 1. So let me state it in n equals 1 because it admits a more classical description first. So these are going to be, well, possibly differential graded, what are called vertex Lie algebras. So if you're familiar with the theory of vertex algebras, a vertex Lie algebra is sort of a part of that, which is sort of what captures the polar part of a vertex algebra. And higher n, well, this guy is equivalent to some higher version of these. Version of vertex Lie algebras. So I don't want to spell out what that is, but there's some generalization of this notion, which also admits a kind of a linear algebraic description, although it becomes a little bit harder because things become more derived. But never mind that. So let me tell you what this theorem gives in the examples, in some of these examples. So say M is it's G bundles, and then let's pick a G bundle. I'm going to call it P now for principal G bundle. G of X, and consider rem hat at P. And let me pick the trivial one, just for simplicity. So then, under this correspondence, well, this is going to, so these are, you should think of as some kind of infinite dimensional Lie algebras. So I will describe what it corresponds to in these kinds of terms. So this is going to correspond to the affine Kac-Moody Lie algebra. So for G, so you take the Lie algebra of G, and there's a loop version of this. So that's hopefully a kind of a familiar infinite dimensional Lie algebra. And the second example, which kind of is already a formal module problem. So if you look at deformations, then this corresponds to the Virasoro algebra. So this kind of makes it explicit, for instance, that, and this is an n equals 1. Well, both of these examples are n equals 1 examples. So this sort of makes explicit the relationship between the Virasoro algebra and the moduli space and the deformation theory of the moduli space of curves. So that's nice. Let me tell you in a few words what goes into kind of establishing such a statement. So the key kind of new observation, just really an enhancement of something Bailenson and Drinfeld did, is that we can build something called a factorization space. So say M is a continuous formal moduli functor. So we have a kind of a point, let's call it P, inside M of X, and well, the formal completion is the same by this assumption that M was formal. So we can consider for, let's say, X, well, let's say it like this. So suppose S is a finite subset. So if we have a finite subset of this variety, we can consider, let me call this space G. I'm going to suppress X now from the notation, so it doesn't get too bad. So consider this kind of space, which is going to be the fiber product of M of X with M of X crossed over its value at the complement of S. This kind of open variety. So in the case of G bundles, you should think of this as two G bundles on X, together with an isomorphism over the complement, over this open part. Oh boy, I'm sorry. That's not what I meant to say. I meant to say take this point. So again, in the case of G bundles, and the point being the trivial G bundle, you take a G bundle together with a trivialization on this thing. And we can the point is, there's a space which parameterizes these finite subsets. So we can consider, so Ron of X is a space parameterizing finite subsets. And so really we have a but because of our assumption that these functors behave well in families, what we obtain is really something over the Ron space. And it has a kind of a remarkable structure. So the remarkable extra structure that this has is, well, let me illustrate it in the case of 2 points. Suppose S is x comma y inside of X, and these are distinct points. Then what we have, and this just follows from the sheaf condition, is that if I look at it over X, so this, maybe write like this, sub S. So if I look at this this space over X, then this is X comma Y. Then this is then there's a natural isomorphism between this and the product of this at X times this at Y. And this, again, behaves well with, in general, if you take a disjoint union of two subsets, then this is going to be a product. So such a thing is called a factorization space. And so the vertex Lie algebra. So the underlying, at least the underlying vector space of the vertex Lie algebra, let's call it theta sub m comma, oh boy, p, right? This is the tangent space of this guy at some single point. And the I guess a remark is that the choice of point doesn't matter, and that's essentially because of that sheaf condition. So this at least is the underlying vertex Lie algebra. So maybe I should say that in the case of moduli of G bundles, and in dimension 1, this G of M is what's known as the affine Grassmannian, which is a very well studied space, and it is very important in the geometrical England's program and things like that. But let's not go in that direction. So now we can use this kind of thing to if we have a non-formal moduli problem, as before, we can try to study d-modules on it in terms of this deformation theory. So next, we can study d-modules on f of x. And so by the way, G here, really, I'm thinking of it as f and Grassmannian. That's what the G stands for. The next thing I will conveniently denote by H, which also stands for something. I'm thinking of these as a version of the Hecke the Hecke operators in number theory. So H of M. So this is going to be again, it's going to be over the run space, and this is going to be the thing I wrote down before. X cross M of minus S. Now we don't fix the second point, and sorry for. So not necessarily formal. So I'm not assuming M is formal. Basically, I'm going to consider this kind of thing, and then if I fix a point of M, this is going to be let's say in this coordinate, then this guy is going to be a, let's take the formal completion at the diagonal, then this is going to be a family of formal moduli functors, or formal moduli spaces rather, over, so this maps actually to the run space as before. In fact, we have this groupoid. I write it like this, H of M. Mapping. There are two maps, the two projection maps, M of X, across the run space. 1, 2. And we, let's remember this projection map. So sort of, in some sense, a refinement of the theorem I just stated is that there's an adjunction between sort of H equivariant sheaves on this guy, M of X cross run, X. So again, these are just sheaves here, so that the two pullbacks become identified in a coherent way. So now it's not an equivalence, but they're adjoint functors. It will be a localization. So let's call this functor lambda and this functor rho to d modules. M of X. Such that this functor rho, the right adjoint, is fully faithful. So in other words, this lets us these are not quite equivalent, but this lets us embed the theory of d modules into these guys. So, a formal consequence of this is if you go here and then you go here, you get back what you started with. So this is a way of sort of in a local to global way of describing d modules on this moduli space. And so, very briefly, in the last few minutes, let me try to sketch an application of this, so that all of this doesn't seem like hogwash.
I was going to ask you that, but I was afraid.
Yeah. Well, I think I'll get to say less about it than I would have liked, but
it sounds beautiful, however.
So the application that I want to describe is that of the Witten genus. So what sort of thing is a Witten genus? Well, it's some procedure that Witten defined using quantum field theory, which takes some. So this is a smooth manifold. So no longer are we in the realm of algebraic geometry for a moment. Let's say of dimension 4k, with what's called a string structure. I'll say more about that in a minute. So then what it assigns to is a modular form, and well, at least assuming some condition on vanishing of the first Pontryagin class, it's going to be a modular form of weight 2k. So, so this is what, and it's a genus in the sense that it's an invariant of the cobordism class of the manifold. So, for instance, if M is the boundary of some 4k plus 1 dimensional manifold with an appropriate notion of string structure, then the Witten genus vanishes. If you take a disjoint union of two things, then it's the product, and so on. So maybe. I really meant to say some here. So that's so it's kind of a very cool construction from conformal field theory, and it has relations to the generalized homology theory of topological modular forms. But let me just say that, well, so in the when M is Kahler, so compact. So when M is Kahler, so in particular we can make it an algebraic variety. So now we're back in the realm of an algebraic geometry, so a string structure. So this corresponds to, so giving M a string structure, this is the same as a trivialization of a certain characteristic class, which is called Ch2 of M, which is, I hope I get this right, it's the square of the first term class, yes, 1/2 the square of the first term class plus the second term class. So we trivialize this characteristic class, and then we're going to associate the Witten genus. So let me give, using this kind of theory that I described, let me sketch a construction, which I should mention is really a recasting of Kevin Costello's construction of the Witten genus. So recasting. Also, it's a modular form. So the way we're going to describe it is, well, it's not, you can think of it as something like a function on the space of elliptic curves. Although it's not quite a function, but it is a function on the space of elliptic curves together with a one form. So E comma omega will produce some number. Genus M of E omega. And, there's some dependence on omega that tells you about which weight this is. So this is the kind of a thing that I will describe. So to do that, I should say something. There is such a thing as the CDO, so algebra. So this is maybe the vertex algebra. Of chiral differential operators. So I don't think I have time to say anything about what that is, but there is some chiral algebras. But in terms of the thing I described, what it does is it produces for you a such a thing. So a CDO. What it does is it gives a So the relevant M, first of all, is going to be maps from blank into this other M. I'm sorry about the poor choice of notation. So that's going to be the relevant continuous moduli problem, and we're going to plug in curves. In particular, we're going to want to plug in an elliptic curve. So I want to plug in elliptic curves. Here. So far we haven't used anything about an elliptic curve. But what a CDO does for you is that it gives an H of M equivariant sheaf on this maps from an arbitrary curve into M across the run space, such that it's just O. On the underlying sheaf is just O. Just O maps so across. Well, really it's right about left versus right. So it gives an equivariant structure. And this equivariant structure on the structure sheaf, and in particular. So applying this functor lambda, what we obtain, the structure of a right D module on the structure sheaf of this moduli space. So an O of maps from X into M. So usually the structure sheaf only has the structure of a left D module. There's a canonical such, and really a unique one in some sense. But here we're doing something different, which is we're getting a right D module structure, and such a thing. So you can sort of just formally translate this. This is the same as giving what's called a projective holomorphic volume form. So a holomorphic volume form is a section of the sheaf of holomorphic top forms. A projective one is one which is locally defined up to a constant. Okay, great. So now take X to be E, an elliptic curve. And then again, we're going to consider maps from E into the target. So in physics language, this is like a sigma model, some kind of a holomorphic sigma model. So rather than looking at the whole space, let's restrict to the. So this splits into a bunch of components given by degree. So this is the degree 0 component. So maps of degree 0 are just points of M, essentially. So it looks like this is just M, but that's not quite true. This has an interesting derived structure. So you can think of it, so what this is going to be isomorphic to, you can think of it as a derived or a supermanifold. And this isomorphism is given by choice of that omega. Of the one form on the elliptic curve. This is going to identify with the odd tangent space of M. And so what do we get? So now we have from all of this we've obtained a projective holomorphic volume form on the odd tangent space of M. So I should mention that the functions on the odd tangent space of M, this is just the direct sum over n of M k, let's say, the kth cohomology of M with coefficients in omega k. So omega k is just k-forms, holomorphic k-forms. So in particular, it contains, if M was dimension 4k, so in particular, this projects down to h4k of x, omega 4k. So these are just volume forms on x. So what some calculations of Kevin Costello imply is that when restricted to this odd tangent space, so let's call this alpha tilde. So alpha tilde lifts to an actual holomorphic volume form. And in this case, the Witten genus, like this elliptic curve. So this is just the integral. Let's call this alpha. So this is just the integral over this odd tangent space of alpha. There is a theory of integration for these kinds of spaces, but in this case it can be described very explicitly, which is there's a canonical identification between the structure sheaf and the sheaf of top forms. And so this procedure of integration just works as follows. You project to this space, and then you integrate on, this is M. And then this is something you can integrate on M. That's going to be that integral. All right, I'll stop here.
Any questions? Okay, good. Let's thank our speaker one more time. Okay, thanks very much for the great talk.
Yeah.